Good day everyone. Today I will be presenting on the topic of classification of vibration. This presentation is part of the course Me22088 Vibration and Noise Control by myself, C. Sendamarikannan, Associate Professor at the Department of Mechanical Engineering, Sri Venkateshwara College of Engineering. Let's start with the basic concepts of vibration. Vibration refers to any motion that repeats itself after an interval of time. Vibratory system consists of three main components: spring, elasticity, mass or inertia, and a damper. These components play crucial roles in the transfer of potential energy to kinetic energy and vice versa to maintain the vibrating motion. Spring or elasticity provides the restoring force that brings the system back to its equilibrium position when displaced. It stores potential energy when compressed or stretched and releases it as kinetic energy when returning to its original shape. Mass or inertia. The mass component represents the object's resistance to change in motion. It stores the kinetic energy when object is in motion. The inertia of the mass determines how much force is required to accelerate the object. In this vibrating system, mass oscillates around the equilibrium position due to the interaction with the spring. The third component is damper. Damper provides resistance to the motion, dissipating energy in the form of heat. This component reduces the amplitude of vibrations over a time, preventing the system from oscillating indefinitely. Dampers are essential in real-world applications to control vibrations and ensure stability. Examples include shock absorbers in vehicle and dampers in building structures. Next, we will discuss the degrees of freedom. Degree of freedom is the minimum number of independent coordinates required to determine completely the position of all parts of a system at any instant of time. For instance, single degree of freedom can be a simple slider crank spring mechanism where only one coordinate is needed to describe its motion. Another example is a spring mass system where the motion of the mass can be described by a single coordinate. Similarly, for a pendulum, the motion of the pendulum can be described by a single coordinate, that is theta. In this slide, we classify vibration based on the number of degrees of freedom. Previously, in the previous slide, we seen 1 degree of freedom system. In this slide, we are seeing the 2 degree of freedom systems. 2 mass spring system. In the system, 2 masses M1, M2 are connected by 2 springs. The motion of each mass is described by coordinate x1 and x2. The interaction between the masses and the spring create coupled vibrations where the displacement of one mass affect the another mass. 2 rotational inertial system. Here 2 rotors J1, J2 are connected by a torsional spring. The angular displacement are represented by theta 1, theta 2. The torsional spring provides a restoring torque and system vibrates torsionally, that is twisting. 2 mass damper system. This system consists of 2 masses M1, M2 connected by dampers and springs. Displacement of each mass is described by x1 and x2. Dampers provide energy dissipation, reducing the amplitude of vibration over the time. So in this system, once again we need to describe the system using 2 degrees of freedom, that is x1 of this mass and x2 of this mass. Moving on to more complex systems, we have 3 degrees of freedom systems. That is the first example, 3 mass spring system. This system involves 3 masses, namely M1, M2, M3 connected by 4 springs. Motion of each mass is described by coordinates respectively as x1, x2, x3. The interaction among the masses and spring results in more intricate vibration patterns where the displacement of one mass influences the others. The second one is three rotational inertia systems. In this example, three rotors J1, J2, J3 are connected by torsional springs. Angular displacement θ1, θ2, θ3 exhibits torsional vibrations, each rotor's motion affecting the others. Three damper mass system. This system consists of three masses M1, M2, M3 connected by dampers and springs. The displacements are described by x1, x2, x3. Dampers provide energy dissipation, ensuring the vibrations reduce over time and preventing indefinite oscillations. Infinite degree of freedom systems are known as continuous or distributed systems. These systems are more complex because they involve an infinite number of coordinates to describe their motion. Examples include beams and plates. By increasing the number of degrees of freedom in a vibration analysis, we can achieve more accurate results. These systems are crucial in engineering as they model real-world structures more accurately. From basic concepts of vibrations we are moving to classification of vibrations. Free vibration occurs when a system is left to vibrate on its own after some initial disturbance. Forced vibration, on the other hand, occurs when a system is subjected to a repeating external force, such as oscillation of a diesel engine. Resonance occurs when the frequency of the external force coincides or matches with any one of the natural frequency of the system, potentially which causes large amplitude vibrations. In this slide, we will classify vibrations based on energy dissipation, undamped vibration and damped vibration. Undamped vibrations occurs when no energy lost or dissipated in friction or otherwise resistance during oscillations. Example, pendulum clock. Damped vibrations happen when energy is lost or dissipated in friction, such as in a car suspension system where shock absorbers dampen the motion to ensure a smooth ride. In this slide, we are classifying the vibration into linear and nonlinear vibrations. Linear vibrations occur when all basic components of the system vibrates linearly. Guitar string is a good example where the restoring force is proportional to the displacement. Nonlinear vibration occurs if any of the components behave nonlinearly. A prime example is earthquake response of a building. During an earthquake, the forces acting on the building don't have a simple direct relationship with the resulting displacements. Materials and structural elements exhibit complex interactions that result in nonlinear behavior. Amplitude variation with respect to time is shown in this graph. When an earthquake strikes, building experience oscillations with varying amplitude over a time. Initially, the amplitude of vibration increases rapidly as the seismic waves exert forces on the structure. As the earthquake progresses, the amplitude may fluctuate due to the varying intensity of seismic activity. Eventually, as the seismic waves subside, amplitude of vibrations decreases and the building gradually returns to its equilibrium state. This graph helps visualize the nonlinear behavior of buildings during an earthquake, highlighting the complex and unpredictable nature of seismic vibrations. Lastly, we will classify vibrations as deterministic or random. Deterministic vibrations occur when the value or magnitude of the excitation, force or motion acting on a vibrating system is known at a given time. An example is heartbeat. Heartbeat pumps is regular, rhythmic in pattern, creating predictable vibration that can be measured as a pulse. Consistent pattern of the heartbeat makes it as a deterministic vibration where the timing and force of a heartbeat can be anticipated. In random vibrations or non-deterministic vibrations occurs when the value of the excitations cannot be predicted. An example of this is random forces acting on a structure due to turbulent winds. This type of vibrations require statistical methods for analysis since the excitation values vary unpredictably over time.